So there's a test on Wednesday, and as usual, I will review today. And as usual, what I typically do is I review backwards. So we'll start with the new stuff, focus on the facts to know from section 5.2 and possible proofs to be able to do. And then we'll work backwards through chapters 4 and 3. So let's start with those facts in section 5.2. I didn't quite have time to actually get to those last Friday. Let's just state the main theorems. Theorems to know from section 5.2. One is that if a function is Riemann integrable on the interval that you're considering, then it must also be bounded. A Riemann integrable function on the given interval, then f must be bounded on that same interval. The contrapositive of this is what's perhaps more useful. If a function is not bounded on the interval, then it can't be Riemann integrable on that same interval. So if you know you've got a function that's not bounded on the given interval, it's not Riemann integrable according to our book's definition. Word of warning, we do sometimes integrate functions that are unbounded on intervals, but when we do that, technically speaking, they are improper intervals. Take this example. Integrating x to the negative 1/2 from 0 to 1. That function is unbounded on the interval from 0 to 1. It's not even defined at 0, though that's not a real big deal. We could define it to equal something at 0 if we wanted to. But this this thing is thought of as an improper integral like that does end up converging. Go ahead and calculate it here. If we let the lower limit approach 0 from the right, the antiderivative of x to the negative 1/2 is going to be x to the positive 1/2 over 1/2, or 2 square root of x. This limit definitely exists. N equals 2. The improper integral converges. That does not contradict this fact. This is not an integral according to our book's chapter 5 approach. This is a different kind of integral. It's an improper integral. It's a limit of ordinary integrals. The limit happens to exist. So we would say this integral does equal 2, but that does not contradict number 1 here. It's a different kind of thing. Second property to know is that if your function is continuous, that's a sufficient condition for Riemann integrability. If f is continuous on the interval from a to b, then f is Riemann integrable on that same interval. So one example of a sufficiently nice function to be Riemann integrable is the class of continuous functions. All continuous functions on closed intervals are Riemann integrable. Of course, you already know they're bounded too, right? You do. What theorem guarantees that they're bounded? theorem since the last test has a name. What guarantees a continuous function on a closed and bounded interval will be bounded on that interval? I think I heard it.
Extreme value theorem.
Extreme value theorem, yeah. It's also Riemann integrable. Monotone functions are also Riemann integrable. Can I do the dash dash thing? Referring to this line. If you've got a function that's bounded, monotone, either monotone increasing or monotone decreasing, then, okay, I'll do the dashes again. That's referring to this line. Then f is Riemann integrable. If a function's not continuous and or not monotone, does that mean it's not Riemann integrable? No. In fact, we did an example. We did the scratch of the proof for a piecewise constant function over a closed interval that was Riemann integrable. It is technically monotone increasing, the one we did, but it's not continuous. An example like that would be neither continuous nor monotone, but it would be Riemann integrable. If you've got a finite number of jump discontinuities, it's okay. You're still going to be Riemann integrable.
Are these all true for the open intervals as well?
You don't integrate over open intervals, you integrate over closed intervals. Okay? These are fundamental facts to know that you should be able to state on exam 2, or answer a true, false, and or a multiple choice question related to them. There's also another theorem in here that I want you to know, but this one's harder to state, harder to understand, and the proof is the hardest proof of the book. And that's relating the integrability of the function according to the definition of Riemann integrability to a fact about adding up those oscillation values times the delta x's. Remember reading about the oscillation? I haven't talked about it in class. You've read about it. It's not actually a difficult idea. Okay, so this is not the statement of the theorem yet. This is a separate thing here. Given a bounded function, and the interval that it's defined on, you can define the oscillation of the function on that same interval. If the function attains its supremum and attains its inf, technically speaking, it's max minus min. It's a simple idea. Well, okay, it may not attain its max or min, so use sup inf. Take the sup of the function outputs as x varies over the domain minus the inf of the function outputs as x varies over the domain. Which reminds me, don't forget about the notation for this kind of set that I introduced. This notation is in the book. F of I, direct image, where I is the closed interval. We also talked about pre-images, inverse images, 2 names. You should know that notation for the test. What was this kind of thing? Inverse image of J exists whether F is invertible or not. That's an important point. It's just the set of all points in the domain, called the domain I, that get mapped into J. I just was reminded of this when I wrote this down. So I'm reminding you, you should know this notation.
Can you repeat that? Go
go ahead and imagine the function is mapping points in one blob to points in another blob. Okay, that's not the case for real valued functions. They're not blobs, but they're sets on the number line. You got a set over here, J. The pre-image over here, also called the inverse image, is the set of points that get mapped into J. All the x's in I represents that whole blob there, that get mapped into J. This exists as a set whether f is invertible or not. This is a direct image, set of all possible outputs as x varies over the domain. The domain in this case is the closed interval from A to B. Okay, again, I was just reminded of that as something to review. So that's what the oscillation is. Theorem 4 here in my list is related to this. It gives an equivalent condition for Riemann integrability on the closed interval. In the setup, you're given a bounded function on the closed interval. That's sort of the background assumption here. It's an if and only if. F is Riemann integrable on the closed interval if and only if for all epsilon greater than 0, there exists a partition not necessarily a tag partition. It doesn't have to be a tag partition. It can just be any partition. P of the closed interval with norm less than delta. Excuse me. Oh, actually, we don't have to refer to the norm. With the following sum ultimately being less than epsilon. Add up the oscillation of f over each subinterval in the partition times the corresponding length of that subinterval, if that's less than epsilon. In your book, it's theorem 5.10. Yep, page 173. Not a tag partition. I mean, it could be a tag partition, but you're not focused on the tags. This is just a set of points. I goes from 1 to n. That partition the interval from A to B, so it's implicit in this notation that A equals x0, B equals xn, and in between, you've got strict inequalities here. That's in the background. The Riemann integrability is according to our definition of Riemann integrability, back in section 5.1. Essentially, by the fact that this is an if and only if, this is an equivalent condition for Riemann integrability. What does it mean, though? What does it mean geometrically? Draw a picture way over on the other side here. Got a function defined on the interval from A to B and bounded. I drew it to be continuous, but it wouldn't have to be. And you'd like to approximate the area under the graph to within any given tolerance epsilon. That's the way we thought about it with the original definition. So give me an epsilon. Can I find a delta so that if the widths of all the rectangles are less than delta, I can guarantee that the Riemann sum value is within epsilon of the true area? Okay, so I'm not going to try to draw it as accurately as I can here, or try to approximate the area as accurately as I can. I'm just going to draw sort of an arbitrary Riemann sum based on tags. I think I'll mark the tags with X's here. Use the tags to determine the heights of the rectangles. So I'm going straight up from those tags to the function, and the height of each rectangle is determined by the height of the function at the tag. Make my vertical lines first here. Ignore the imperfections in the picture. This one's really bad. Let's go up there. These rectangles don't have to all have the same width. In calculus, we typically make them have the same width. So there's rectangles whose area, when you add them up, approximates the area under the graph. And the idea again being is if f is Riemann integrable, for any given tolerance epsilon, you can choose, well, for any tag partition of sufficiently small norm, the norm of this particular tag partition is probably the length of that interval, which is the biggest interval there. You can make the Riemann sum within epsilon of the true area. And I don't have a formula, I don't have numbers in this graph, so I'm not going to pick an epsilon or anything like that. How is that related to this? Well, certainly for continuous functions, the sup and the inf are attained. You could use max and min instead of sup and inf. On each of these subintervals for this particular partition, you could find points in each subinterval that give you the max and min outputs for the function on that subinterval. Take the first subinterval right here. On that closed interval right there, the function is highest at the right endpoint and lowest right about there. Let me draw a rectangle whose height is the lowest value of the function, and then another rectangle whose height is the highest value. That distance right there is the value of the oscillation of the function over the first subinterval. That distance right there. What about the second subinterval? The lowest values at the left endpoint, draw a rectangle with that height. The highest values at the right endpoint, draw a rectangle with that height. Going all the way down to the axis. The difference between these areas of these rectangles is given by the area of that rectangle. Same with this one. Whose height was that? The height of this one is the oscillation of f over that second subinterval. And the base, delta x1, delta x2, that would continue. We could continue this process. The product of this with this gives you the area of that. The product of this with this gives you the area of that. Again, I could continue the process. Essentially, what you're saying, by the fact that you can make this summation less than any given epsilon, is you can choose your partition in such a way that the areas of these rectangles representing the difference between the areas of the smallest possible approximating rectangle and the biggest possible approximating rectangle, the sum of those areas can be made as small as you like. I found something on the Wolfram Demonstrations project that illustrates Riemann sums pretty nicely. It's by a person named Ed Pegg Jr. Ed Pegg Jr., if you ever watch this, thank you for providing this. to illustrate Riemann sums pretty nicely. You can zoom in on this if you need to. It's a little hard to see there. Is that too big? That's too big probably. Well, yeah, we've got to make it smaller. In this code, you can do left-hand sums, right-hand sums, and midpoint sums. For an increasing function like this, the left-hand sums are going to be too small, and the right-hand sums are going to be too big. But as the number of rectangles gets larger and larger without bounds, certainly they both end up giving you a good approximation to the area under the curve. And if I toggle back and forth between the left and right, the left-hand ones, again, are using the left endpoint of each subinterval to determine the height of the rectangle. Because the function's increasing, the min, the inf, is going to occur at the left endpoint, and the sup is going to occur at the right endpoint, and the distance between the sup and the inf, the length of that little vertical line segment right there, that's going to be the height of a rectangle that gives you the difference between the left-hand approximation and the right-hand approximation for that interval. And again, this condition is saying if you add all of those areas up, these can be thought of as areas of rectangles. Back over here, you can make it as small as you like, and that's equivalent to Riemann integrability. In fact, this theorem, this fact, the equivalency between the Riemann integrability and this fact here, makes these facts easier to prove, well, especially the first and second one, or excuse me, the second and third one. The book proves the second one, and they use uniform continuity of a function on a closed interval, of a continuous function on a closed interval to do it. Could that proof show up on the test? I think so. It's not too hard. I mean, I think it'd be difficult to think of on your own without seeing the book's proof. But if you study the book's proof, it's not real long, about 5 sentences or so. It's not too hard once you believe this fact here.
Which one?
It's the proof of this one here, Theorem 5.11, page 175. It uses the uniform continuity theorem right away, second sentence, after let epsilon be greater than 0. Since f is uniformly continuous on the closed interval, they don't even say it's the theorem, but that is the uniform continuity theorem that you're using. And they prove that given any epsilon, they start by saying let epsilon be greater than 0, there is a partition where this is true. You should study that proof. That's I think well, you know what, I guess based on what I said, it can't be on this exam, but it could be on exam 3. Okay. For exam 2, I said just definition statements and theorem statements from section 5.2. But you should still study it anyway. It could be on exam 3. I will not put the proof of this fact on exam 2 or 3. Okay? That's the hardest